Chemical reactions involve the making and breaking of bonds. In order to understand much of organic chemistry, we first must be able to describe bonding within a molecule itself. There are several models of bonding in organic molecules that have, at one point in their history, achieved scientific consensus. Each of them has their own pitfalls, but they are all useful to organic chemists even today. Two of those models, the Lewis model and the valence bond model, will be reviewed here. The Lewis model of bonding states that the sharing of two electrons by more than one atom will permit each atom to have a stable closed shell electron configuration. This is otherwise known as the octet rule. When forming bonds, atoms either gain, lose, or share electrons to achieve a stable electron configuration characterized by 8 valence electrons. Gain or loss of electrons results in ionic bonding, while sharing of electrons results in covalent bonding. If we were to tabulate the first row elements according to their number of valence electrons, number of electrons needed for a complete octet, the number of covalent bonds made, and the number of lone pairs, we see some obvious patterns emerge for covalent compounds. For hydrogen, we know that it has one valence electron. Since its complete valence shell can contain a maximum of 2 electrons, it makes a duet instead of an octet, and the number of electrons needed to form this duet is a single electron. This means it can make one bond with no lone pairs. Carbon has 4 valence electrons. It needs 4 more to complete an octet, so it makes 4 bonds with no lone pairs. Nitrogen has 5 valence electrons, which means it needs 3 more to complete its octet, so it makes 3 bonds and has 1 lone pair of electrons. The same pattern emerges for oxygen and fluorine. But if we look at lithium, we will notice that it has 1 valence electron. It needs 7 more electrons to complete its octet, but instead of making 7 bonds, it loses an electron to generate the noble gas configuration of helium. This is no longer covalent bonding, but rather ionic bonding. A Lewis dot structure can be generated by knowing the type and number of atoms in a molecule. For example, for the molecule with the molecular formula CH4O, we can add up the number of valence electrons for each atom and then arrange the atoms such that a reasonable dot structure can form. In the case of this molecule, methanol, the carbon atom will make single bonds to 3 hydrogens and an oxygen atom, while the oxygen will have single bonds to carbon and hydrogen with 2 lone pairs. You should try to draw Lewis structures for the following molecules on your own. Pay close attention to the number and type of atoms and the overall charge for each molecule. So what do Lewis structures look like in 3 dimensions? We use valence shell electron pair repulsion, or VSEPR, to predict geometries. In essence, an electron pair, existing either in a bond or as an unbonded lone pair, associated with an atom, will lie as far away from the atom's other electron pairs as possible. This is due to electron repulsion, like charges repelling. An example is CH4, or methane. Electrons in the CH bond will repel, so the molecule will adopt a geometry that allows the electrons in those bonds to lie as far apart as possible. In methane, this would be a tetrahedron, which has bond angles of 109.5. Other possible geometries include bent, trigonal pyramidal, linear, and trigonal planar. Try to draw the Lewis structures for each of these molecules shown. The second major model of bonding is the valence bond model. This model is a response to Lewis structures, which are convenient, but not the whole picture. In summary, electrons have wave-particle duality, so we can describe bonding as an interaction between waves. When 2 waves overlap in phase, they reinforce each other to create a new wave or a chemical bond. The best example is molecular hydrogen. When the electrons in two 1s orbitals overlap, the waves reinforce and a new orbital is created. This new bond comes from reinforcing 1s orbitals and is known as a sigma orbital or sigma bond. This model is limited, however, since it does not account for the reactivity of molecules. The third model of bonding, governed by quantum mechanics, is known as molecular orbital theory, and we will discuss this more in depth in class.